In this video, we're going to discuss quantum theories of chemical bonding. One of the most important developments in chemistry came in 1916 when G.N. Lewis developed his concept of chemical bonding from the standpoint of sharing electrons and transfer of electrons between atoms fulfilling so-called octets. So for example, in the F2 molecule, we can consider fluorine to be bound to another fluorine through a shared electron pair bond, and the remaining electrons surrounding each of the fluorine atoms in so-called lone pairs. A huge amount of chemistry could be understood using Lewis's concept. However, there were some aspects of this that were very confusing at the time. Chief among these was this electron pair bond. From the standpoint of electrostatics, it makes no sense that electrons would form a pair bond, because essentially what we're doing is we're localizing two electrons close together in space. And one would expect there to be a huge amount of electron-electron repulsion, making this a repulsive as opposed to an attractive effect, bringing those two together. And it really took until the development of quantum mechanics in the 1920s, and then the application of quantum mechanics to chemical bonding in the 1930s and later, to explain the origins of this electron pair bond. In this video, I'm going to introduce you to the two main techniques that are used to describe bonding in molecules using a quantum mechanical approach. This is valence bond theory and molecular orbital theory. We're going to start by reminding ourselves of a few aspects of the Schrodinger equation. In its simplest form, we can write the Schrodinger equation in terms of H psi equals E psi, where H is our Hamiltonian operator, and it contains information concerning the potential and kinetic energy of the system. E is the energy of the system for a given state, and this represents the only observable in the Schrodinger equation. So this is an important thing to understand, is that of all the different terms that you see in the Schrodinger equation, the only one that is actually experimentally observable is the energy. Psi is what we refer to as a wave function. Psi yields solutions to the Schrodinger equation, and there are an infinite number of wave functions that can give a valid solution to the Schrodinger equation. For our purposes, the wave function gives us information about the electrons in a specific region of space. With different values of psi yielding orbitals. Now, although the Schrodinger equation in the form that I've written it above seems to be very simple, it's actually mathematically a very daunting equation to tackle and solve exactly. In fact, it is impossible to solve the Schrodinger equation for systems that contain more than one electron. So essentially, every system that's chemically interesting, it's impossible to solve the Schrodinger equation exactly. Therefore, a number of approximate methods have been developed to approximate the solution. To the Schrodinger equation. You have already been introduced to some of these approximations without even realizing that they were approximations. For example, anytime you drew an orbital for an atom that contained more than one electron, you're in fact drawing orbitals for atoms that contain single electrons. You've been drawing hydrogen-like atomic orbitals. In the remainder of the video, we're going to introduce two more approximations, valence bond theory and molecular orbital theory, which are approximate ways of solving the Schrodinger equation for multi-electron systems, molecules that contain more than one electron. Now, when I say that these are approximations, I'm not saying that these aren't rigorous. They're actually incredibly mathematically rigorous, and we can get very close to the actual solution to the Schrodinger equation. It's just that you need to keep in mind that these are approximate solutions to the Schrodinger equation, no matter how accurate they are. We're not explicitly solving for the Schrodinger equation with any of these methods. We're going to start by discussing valence bond theory. Valence bond theory was originally formulated by Heitler in London in the late 1920s and was later popularized by Pauling. In valence bond theory, what we do is we focus on the electrons, and specifically electrons belonging to individual atoms and how they interact to form bonds. It is because of this interaction of electrons to form so-called valence bonds that's given this misunderstanding of valence bond theory as simply being quantum Lewis theory. Although it's conceptually a nice starting point to think about these different valence bonds in terms of Lewis structures, it actually leads to a number of misunderstandings of valence bond theory. So we're going to eliminate this idea that valence bond theory is simply quantum Lewis theory. It's actually much, much more than that. For our development of valence bond theory and then molecular orbital theory, we're going to consider one of the simplest molecules, the H2 molecule. The way we're going to think about this is we're going to think about two isolated hydrogen atoms separated at an infinite distance. And what we're going to do is we're going to bring these two hydrogen atoms together and eventually form an HH bond. So we're going to bring these two hydrogen atoms from infinity, we're going to bring them to their bonding distance, and then we're going to bring them in to be shorter than their bonding distance, which is 0.74 angstroms. What we're going to do is we're going to label these hydrogen atoms as HA and HB. And what we're going to do is we're going to give an electron to HA, being a spin up electron, and we're going to give an electron to HB, being the spin down electron. And we're going to bring these together, and eventually we're going to form that electron pair bond. If you go through and work through the math, you can come up with a wave function for this. And we're going to give this the wave function psi1. Now, because electrons are indistinguishable subatomic particles, there's no reason that the spin up electron has to be associated with the nucleus for HA and the spin down has to be associated with the nucleus for HB. In fact, we can write this like this, bring these together, and form our electron pair bond like this, and come up with a new wave function, psi 2. In order to properly describe the bonding in H2, both psi 1 and psi 2 need to be considered. If you only consider psi 1 or psi 2, then the physics just simply doesn't work out. So we have our two wave functions, and what we need to do is we need to take linear combinations of these wave functions. And when we do this, we'll get two different wave functions out of them. One of these we're going to label as psi plus, and this is equal to psi 1 plus psi 2 with a normalization coefficient in front of it that we're not going to go through and describe right now. The other one is psi 1 minus psi 2. We can go through and plot the energy of these two wave functions as a function of bond distance. Just to give us a reference, the dissociation energy for H2 that's been measured experimentally is equal to 452 kilojoules per mole, and the experimental HH equilibrium bond length is 0.74 angstroms. Going through and plotting psi plus for H2, we get a curve that looks like this. Where that distance is 0.87 angstroms, and the dissociation energy that we obtain is approximately 310 kilojoules per mole. So we're close to the equilibrium bond length, but not spot on. We're also close to the bond dissociation energy for H2 with this description, but it's not exact. Going through and plotting psi minus, you get something that looks like this. So as you bring these two nuclei together, the energy of the system just begins to increase and increase. This description that we have actually has some physical meaning to it. So this psi plus that we've plotted, what this is bringing two anti-parallel spins together. What we've done is we've plotted the covalent part of this valence bond wave function. What this psi minus is this is bringing together two parallel spins. Two parallel spins can't combine to form an electron pair bond. That would be a violation of the Pauli principle. So this is just bringing together two non-interacting hydrogen atoms closer and closer and closer together. And that is a repulsive interaction. You go up higher and higher in energy as you bring in these two closer and closer together. It's this covalent interaction where we have the two anti-parallel spins, where we don't have a violation of the Pauli principle, where we can form that electron pair bond. Even though the covalent description gives a reasonably close value to what we observe experimentally, we can make improvements on this. And one of the biggest ways we can make improvements on this is we don't consider the two electrons to be associated with the nucleus for HA and the nucleus for HB, but instead we can put both electrons associated with either HA or we can associate them with HB. In other words, we can come up with an ionic wave function. So, for example, we can come up with psi3, which corresponds to the 2 electrons associated with HA, making it a hydride, and none associated with HB, making it a proton. We can come up with psi4, which is a proton associated with HA, both electrons associated with HB, making it a hydride. And the overall ionic wave function would be psi3 plus psi4, and of course we would have to have some normalization factor in front of that to complete it mathematically. We can now go through and write out the complete valence bond wave function as just simply being the covalent wave function plus the weighted ionic wave function. When we do this and we plot its energy and equilibrium bond length, we now get something that matches the experimental bond length of 0.74 angstroms and the bond dissociation energy of approximately 450 kilojoules per mole. So what valence bond theory reveals about the HH bond is that H2 is both described in covalent terms with some percentage of ionic terms. So the overall valence bond wave function is approximately 90% covalent and 10% ionic. You have to consider this ionic contribution to match the experimental data. So valence bond theory can give you additional insight into the nature of the HH bond. An alternative method for obtaining approximate solutions of the Schrodinger equation for multi-electron molecules is so-called molecular orbital theory. Molecular orbital theory was originally developed by Mulliken and Hund. And because it's mathematically and computationally a bit easier to implement than valence bond theory, it's become the dominant way in which we describe solutions quantum mechanically these days. MO theory, unlike valence bond theory, does not try to describe systems using interacting electrons. Instead, what one does is one derives orbitals, wave functions, for the molecule as a whole. So what one does is one generates molecular orbitals. In practice, the way in which we do this is we generate so-called linear combinations of atomic orbitals. So when we generate a molecular orbital, what we do is we take the individual atomic orbital wave functions for all of the atoms in the molecule and we weight them and generate linear combinations. So C1, V1 plus or minus C2, V2, all the way up until you've accounted for all of your atomic orbitals. What we're going to do is we're going to generate the molecular orbitals and a MO diagram for H2. And the way we're going to do this is we're going to look at the 1s orbital for HA, adding together and subtracting from the 1s orbital for HB. What we're now going to do is we're going to generate linear combinations of our hydrogen 1s orbitals for H2. So we can come up with one wave function that's going to equal some normalization constant, C1 1s plus C2 1s. Here, because C1 equals C2, we're going to say that this wave function, which we're going to call psi1, is going to be approximately the 1s orbital plus the 1s orbital. Here, psi2 is the out-of-phase combination, so it's going to be 1s minus the 1s orbital. We can look at this visually. So with psi1, what we're doing is we're taking a 1s orbital and we're adding together another 1s orbital, and when we do this, we make a molecular orbital that looks like that. When we look at psi2, what we're doing is we're taking a 1s orbital and we're adding together a 1s orbital that has the opposite phase of that s orbital. This is the same thing as subtracting that in phase 1s orbital. And when you do this, what you get is a molecular orbital that looks like that. This in-phase combination, psi1, is a bonding orbital. It's a bonding combination. This is going to be lower in energy than our starting 1s orbitals. This out-of-phase combination is what we call an antibonding orbital. It's going to be higher in energy than our starting atomic 1s orbitals. Now, if you remember back, what we said is that the square of the wave function tells you where the electron is in three-dimensional space. So the probability of finding the electron in three-dimensional space. What this says is that if we examine our bonding orbital, psi1, the probability of finding electrons that are described by that orbital is in between the two nuclei. This is in fact consistent with what we would have envisioned from our Lewis structure, where that electron pair bond would locate those two electrons between the two nuclei. So in that sense, MO theory is validating a prediction that we would make using simple Lewis theory. It is often convenient to visualize the energies of the molecular orbitals and sometimes how the molecular orbitals are formed through interaction of the atomic orbitals through something called a molecular orbital diagram. So in a molecular orbital diagram, what we're going to do is we're going to put energy on one axis, and we're going to place our hydrogen 1s atomic orbital functions on two sides. What these energies signify are ionization energies. So these would be the ionization energies of the hydrogen 1s electron. And what we do is we combine these together. We make a lower energy bonding orbital. So that's psi1. And then the higher energy antibonding orbital. At this point, we're going to consider our electrons. And we have one electron from one hydrogen atom, one electron from another hydrogen atom. And so we're going to place these together like this. Okay, so we're going to place 2 electrons in psi 1. Okay. An important concept that we're going to use in this class is a concept of a bond order. A bond order is simply equal to 1/2 times the number of electrons in bonding orbitals minus the number of electrons in antibonding orbitals. So the bond order for H2 is equal to 1/2 of 2 minus 0, so that equals 1. A way in which we can think about this is that there's single bond character between the 2 hydrogen nuclei. So the H2 bond is a single bond. However, one should be careful and not stretch that analogy too far, equating bond order exactly with single versus double versus triple bonding. But one thing that you can do is make conclusions regarding bond strengths and bond lengths. So if you're looking at some XX bond and you keep the nuclei the same, that the higher the bond order, the stronger the XX bond is going to be, and the shorter the XX bond will be. Furthermore, you can make conclusions that if a molecule has a bond order of 0, then the 2 nuclei that are describing that bond are going to be non-bonding. They're not going to come together to form a bond. We're going to end this video by talking a little bit about molecular orbital theory versus bond theory. And a question that people often have is, which one is correct? And in my mind, this is not a really great question, because it's akin to saying which one of these 2 colors is the correct color of blue. They're both colors of blue. They're both different representation of the color of blue, and neither is correctly the color of blue. Because MO theory and valence bond theory are both approximate solutions to the Schrodinger equation, both can be viewed as being incorrect, just as both can be viewed as being correct. They're correct in as far as the approximations that they make. And in fact, at their limits, valence bond theory and molecular orbital theory reach identical solutions to the Schrodinger equation. Instead, we should compare MO theory versus valence bond theory and ask what they're good at and what their weaknesses are. Up until about the 1950s, valence bond theory was really the preferred method for describing bonding quantum mechanically by chemists. And the reason for this is it focuses on electron-electron interactions. In other ways, it describes bonding in the way that chemists think. And therefore, the theory was very naturally set up to give chemists an instant view of bonding in a way in which we think about bonding. MO, on the other hand, does away with these electron interactions, so you don't consider these electron-electron interactions to derive a view of bonding. Because of this, it's very you have to do some thinking in order to go between an MO description and the way in which we think about chemical structure and reactivity in a Lewis sense of the word. Now, the flip side of this is that MO theory is rather easy to set up and get qualitative and quantitative answers quickly. In contrast, valence bond theory, to do correctly, is rather complex. So you saw, looking at H2, we had to come up with all these valence bond wave functions and weight these together properly in order to come up with a correct description of H2. And that was just for H2, just a 2-electron system. This gets really, really complicated really fast. And for example, in order to get the correct description of the photoelectron spectrum for methane, or to determine that O2 has a triplet ground state, you have to actually go through and set up some very complex math to get this using a valence bond description, while in MO theory, it's rather easy to set that problem and get the correct solutions to these problems out. Now, because of its reasonable simplicity in quickly getting chemically useful answers, throughout this course, we're going to focus exclusively on molecular orbital theory and how it relates back to our view of chemical bonding.